Let's do something different here. So I have a ground resistance test set, okay? This is your standard, clamp on ground test set. And, always use the loop. And this is just a calibration loop, just to double check the calibration, kind of like a function check out in the field. And if you read the side of this one right here, it says that it's 5.1 plus or minus 0.1, and she's spot on. So, we're good there. So this thing works. Just don't want to let you think I'm deceiving you. And then we have a fluke meter here plugged in. Now, what I want to do is I want to showcase two different things here. And the first one is going to be how this meter works. And once we get past that, then we can start doing the nuts and bolts for the other stuff, okay? And the other stuff's going to be, I've run into before where people are like, what should I study for my NETA test? And I tell them, basic AC and DC theory. They're like, oh yeah, I got that, no problem. And then I start saying power factor and how to calculate capacitive reactance, and so they're like, that's engineering. No, that's basic AC electrical theory. If you take physics 2 or whatever in your college, it's going to be right there. It's not engineering level stuff, okay? So I just want to kind of showcase how to do that stuff, all right? So, but we need a ground test set. And why do we need this? Well, because this thing doesn't measure resistance. I know that you all think it measures resistance. It does not. It measures impedance, okay? This is not a DC test set. That's resistance. This is an AC test set. So and to prove that, we have this guy hooked up right here. Now we're pushing a little bit of milliamps of current, okay? And how does this thing work? Well, there's actually two clamps inside of here. I'm gonna open up these jaws so you can see it right here. There's two clamps in here, okay? One clamp is going to induce a voltage onto the test specimen. The other clamp is going to measure the current. And then internally, this thing's just going to divide those, okay? And because it's inducing a voltage, that means it's AC. Therefore, it has to be an impedance value, okay? Cannot be DC. So we're going to take this right here. We're going to put it on here. What is the biggest thing about measuring impedance, right? This is saying that the resistance and whether there's capacitance or anything else on this meter, the combined impedance of all this loop is 2.6 ohms, okay? But there's a catch. So this test set operates at about 1 kilohertz, maybe 1.1. It bounces around a little bit, but most ground resistance test sets operate about 1 kilohertz, okay? Why does that make a difference? We're about to showcase why, okay? So 1 kilohertz, well, that makes a big difference, right? If you have a resistive system, no difference. But if you have a capacitive system, the higher the frequency, the lower the impedance of your capacitance, right? Your capacitors look like a short circuit at high frequencies. And then, inductors, this is just a bunch of coil, right? This is a big inductor. Well, not really a big one, but these are just, one's probably half used and the other one's not. So you'll see the difference between them. But inductors at higher frequencies, they're called chokes. That's why in circuits they're called chokes, is because they choke the current at higher frequencies. So at higher frequencies, the impedance of these will go up. At lower frequencies, as you get towards DC, this looks like a short circuit, right? And that's common. If I hook up a battery up to this, it's going to provide as much current as that battery can provide because it looks like a short circuit. Okay, but as soon as I apply it to the wall or anything else, it changes. So let's kind of do the proof in the pudding here. Now, I just wanted to say one thing about this meter right here. I did have it on milliamps at first. I will tell you that most flukes or even like a FLIR, most meters, because they're designed to be used primarily on the power system, they are more accurate and the most accurate at 50 and 60 hertz. When you go outside of those ranges, this thing starts to get really spotty. Its internal calculations are not as precise. So just that's why this thing's jumping all around the place. So don't try to hold that to a higher standard. It's probably going to mismeasure a little bit just because it's at 1 kilohertz instead of the nominal 600 hertz or 60 hertz. Okay, so let's do some stuff right here. Okay, so I have this test set, it's not it, right. It's OL. That sounds about right. So what we're going to do is we're just going to measure, and I have a lot of crazy stuff here. So let's do the first one, okay? This is going to be this guy right here. This was a cool toy. This is just a bunch of capacitors hooked up together. I kind of wanted to make a short circuit demo, and so it's just some leads coming off of it, okay? So this is just a capacitor. So what would you expect this capacitor to look like? Well, it's 1 kilohertz, right? So we're just going to go ahead and we're just going to run this directly to the meter, and we're going to put this right here, and I'm going to hook it up to my trusty, I'll hook it up to this one right here. So we'll go straight to ohms. I'm going to plug this guy in. And when you plug this thing in on ohms, what does it say? Oh, we don't want to do that. Here we go. It's got 0.9 mega ohms, so 962 kilo ohms. This thing is a very high resistance. It does have capacitance though. Okay, and I don't know if this is too high for it. Yeah, it's a lot of capacitors. That's probably going to take a second to figure it out. But it's, yeah, there you go. 2.5 millifarads. It was storing a lot of juice, and we were just discharging it for fun. So it's a big capacitor, very high resistance on a DC test. Okay, these things test on DC. But if I hook it up to the handy dandy, ground test set operating at 1 kilohertz. Okay, how do I hook it up? Well, I'm just going to short circuit the capacitor and clamp on it. It says that it's 0.04 ohms. Well, that just changed. We went from 900 kilo ohms on a DC test to 0.04 ohms of impedance. That is because if you were to go ahead and do the math on it, how do you determine the capacitive reactance of this circuit? Well, it's going to be the impedance of this capacitor is 1 over 2.5 millifarads times 2 times pi times 1.1 kilohertz. If you do the math on that, you're probably gonna get somewhere near there. Okay, so that's how it's working.